Hey there. Let's talk about Newton's law of universal gravitation. Newton's law of universal gravitation, what it says basically is that every object in the universe exerts a gravitational pull on every other object. And we've talked a little bit about this, how, just sitting there, you're exerting a gravitational pull on the chair and the chair's exerting a pull on you. We can go out and Earth pulls on the moon, but the moon pulls on the Earth. And those forces, they're equal in magnitude. So we have the force of the moon on the Earth that's equal in magnitude, but opposite in direction to the force of the Earth on the moon. And this creates the tides on Earth, and it holds the moon in orbit. Anyway, that's Newton's third law, but the universal gravitation says that this happens for everything. So every object, and it's according to this law that the force, the gravitational force exerted by one object on another is equal to this is the universal gravitational constant. And it's this number down here. It's equal to that times the product of the two masses divided by the distance between them squared. Now I wrote it with an R. Sometimes you'll see this with a D. So just the distance between them. We're going to talk about R though, because we're looking at circular motion, and normally when we're talking about gravitational forces, we're talking about orbits. We're trying to analyze those. This formula you'll need to remember. This number you won't. This number is off on it's right there on your equation sheet. Notice the units here. Excuse me. Here we have meters cubed over kilograms second squared. And the way that I wrote it was newtons meter squared kilograms. The difference between these is that they just took newtons, which is kilogram meters per second, and just broke it all out into the units. So anyway, I'm going to leave it like this. But what you're going to see is that when we multiply these units times, up here you get meters squared, kilograms squared, and down here you'll have meters squared. So all these units will end up canceling out. But that's about it. So again, we're going to be looking at, circular motion. So like as the moon goes around, why does it do this? Well, it's because we have some force. We have a net force acting towards the center of the orbit, which gives us some radial acceleration and so on. So all we need to know are the two masses and the distance between them, and we can determine the gravitational force. So let's go ahead and work through a couple examples. So let's go ahead and get the gravitational force between the Earth and the moon. So again, we're looking at, we have the force of the moon on the Earth and the force of the Earth on the moon. I know I'm not drawing these very well, but you get the idea. And then I have some quantities here. I went ahead and just put these up here. So the mass of the Earth is about 5.972 10 to the 24th. Mass of the moon. There's the distance between them. Distances, normally when you look them up, they're going to be given in kilometers, but my gravitational constant is in meters, so you'll need to convert everything into meters. So when you're doing these types of problems, make sure everything's in kilograms and meters, standard units all the time, and we'll end up with newtons as our force. So this is it. So we get our force is going to be equal to either force. Remember, they're just opposite in direction, but equal in magnitude. That force is going to be equal to G, so we'll drag G up here, times the mass of one of them, we'll say the mass of the Earth, times the mass of the moon, and all of that is going to be divided by the distance between them squared. So let's take this one up here. And I'll tell you, oftentimes I forget this squaring because you have all of these numbers and all of these exponents. So please, please, please remember, because it throws everything off. So we're going to take that squared. So what you'll see is the meters squared are going to cancel these meters squared, these kilograms squared, cancel these 2 kilograms. So we'll just be left with newtons. So now the question is, how do we put this in the calculator? So let me show you that real quick. It's pretty simple. So we'll enter this entire thing. So we have 6.67. And then when we do times 10, you can just type that out. You could do times 10 raised to the power of negative 11. So you could type it that way, but you see that little e? So that little e is right here. So I could just do 6.67. It saves a couple of keystrokes. E negative 11. So it just makes it a little easier to type, and then what I'm typing in looks like my answers. And then we're going to multiply that by 5.972 E24 times 7.348 E22. And I'm going to click over and divide that entire thing by, I'm going to go to put this in scientific notation as well, 3.844, and that's got to move, we got 6, 7, 8 to the 8th power. And all of that is squared. Let me go back and put a parenthesis. And you can do this in pieces, you know, that's fine. Squared, enter. So we get the force is going to be 1.98 times 10 to the 20th. 1.98 times 10 to the 20th. To the 20th newtons. You double check that. So 1.98 times 10. And I can check and make sure everything looks good. Yeah, everything looks good. So big force, right? So we have times 10 to the 20th. So how come these don't just slam together? Well, in order to actually change, remember that this is circular motion, so the velocity is in this direction. And to really change both the magnitude and the direction and the magnitude, we got to take into account the mass. So if we use Newton's second law, we can determine the centripetal acceleration. So the force is equal to the mass times the centripetal acceleration. So my centripetal acceleration would just be the force divided by the mass. So I'll just take this quantity and let's divide it by, say, the mass of the moon. So 7.38. So we'll take that same quantity and we're going to divide by 7.38 to the times 10 to the 22nd power. So we have a centripetal acceleration of 0.002. Not very much acceleration. AC is 0.002 meters per second squared. It's very small, very tiny. So in fact, you know, yeah, it's just really small. So it doesn't come slamming down into the earth. So there you go. It's really this type of problem. It's just plug and chug. You may have some other, you know, quantity. Maybe you're looking for the mass of an object or the distance. We'll do one of those here in a second. So let's do this one. What's the gravitational force of a person that's standing at sea level? So if you were just standing, you know, somewhere on sea level, what's the force that the Earth is exerting on you? And I know you're going to want to say 9.8, but remember 9.8 is the acceleration due to gravity, not the force. But we can calculate it. So we get the force of the Earth on me is going to be my gravitational constant times the mass of, say, me. So I'm about 80 kilograms times the mass of the Earth. All of that divided by the radius. And when we talk about the distance, you know, or the distance between the two objects, you know, you might think that because we're standing on the surface, the distance is 0, but it's always measured to the center because, in fact, we're going around in this direction. So we need to find this radius. And the radius of the Earth is a little bit over 6 million meters. So we'll divide all of that by this squared. And that will tell us the force of the Earth on me. And I think I already calculated this one. Yeah, so we get, it's about 785 newtons. Much, much less than the moon. And that makes sense because my mass is much, much less than the mass of the moon. So the force is directly proportional to the masses. So if you have more massive objects, you have a lot more gravitational force, but inversely proportional to the radius. If I was not here, if I was on the moon, then the force of the Earth on me would be much less than this. But now let's go ahead and check the acceleration. So if I wanted to know the acceleration, the centripetal acceleration, I would have my force is going to be my mass times the centripetal acceleration. So the acceleration is going to be the force divided by the mass, which would be 785 divided by 80, which is 9.81 9.81806 meters per second squared. I'm sorry, I said centripetal, but this is the acceleration due to gravity. So that's g, and that's about right, 9.8. That's what we take to be the gravitational the acceleration due to gravity. But how much does the mass matter? You know, what if it wasn't me? What if it was 8,000 kilograms? So, something very, very large. Would that change? No. And you can do the calculations. If you change this 80 to 8,000 and then divide the result by 8,000, you'll get actually the same number. So the mass of the Earth is so great that it overpowers the smaller mass. When you're talking about the gravitational constant on Earth, that's why we consider it to be pretty much constant, because there's nothing big enough to alter it. Yeah. So let's do one more. So say I wanted to know, if I was out in space or I climbed a mountain, how far away would I have to be from the Earth in order to experience half of g? So remember, g is just the acceleration due to gravity. So if I wanted to get to 1/2 of my weight, how far away would I have to be? And again, we can just use this, but this time I'll be solving for r. So I want my force to be 1/2 of the acceleration. So let's see, my force is going to be mass times acceleration. I'm sorry, I'll just put g. And so I want my force to be my mass, which is 80 times 1/2 of g. So I want my force to be, that's 80 times, sorry, I'll just do it here so you can see. So I'll take my mass times 0.5 times 9.8. So I want the force to be 392. So when is the force going to be, when am I going to experience half of the acceleration due to gravity? Well, that will be when the force is 392 newtons. Now to find the distance, I can just plug in over here. So I get 392 is equal to g, let me move this stuff because it's going to get in the way, times m1, which is 80, times the mass of the Earth, and then all of that's divided by r squared. By r squared. You know what, let me back up. I'll come back to this. Because this might be easier. You see how all these numbers are messy? And I don't want to do any of these big calculations. But see, if we just worked with the variables, we would get g m1, m2 divided by r squared. I'm just going to solve for r. So the first thing I would do is divide by g. So I would get F over G equals M1, M2 over R squared. Then I can multiply over here. So I get R squared times F over G equals M1 times M2. And then I would divide by this fraction or just multiply by the reciprocal. So I get R squared is M1 times M2 times G over F. So I just multiplied by the reciprocal. So my distance will be the square root of M1 times M2 times G divided by the force. Now I can just put in my numbers and it'll be nice and clean. So I can put it straight into the calculator. I'll do the square root. Mass 1 is going to be, let's go to parentheses, the 80, my 80 kilograms times mass 2, which is the mass of Earth, which is 5.972 times 10 to the 24th power. And then we divide that all by the force, which was 392. So we get 1.1 times 10 to the 12th. 1.1 times 10 to the 12th. So that's how far I would have to be from the center. So be careful here, because that's how far from the Earth. So that would be my distance from the center. So what I need to do is subtract the radius of the Earth. So I'll subtract that 6.3 times 10 to the 6th minus 6.3 times 10 to the 6th. And we get, yeah, it didn't really change all that much. Not at all, actually. So it doesn't matter. So that's how far away we got to be in meters. Let's compare that to the moon. So distance to the moon. 3.8 times 10 to the 6th, 7, 8 times 10 to the 8th. So I'd have to be past the moon in order to experience half of G. Pretty interesting, huh? And why don't you go ahead and do this one? We'll say you're, just say you're 60 kilograms and your classmate is 75 kilograms. So what's the gravitational force if you're sitting 1 meter apart? So go ahead and calculate that, submit that as your answer for your XP.